Okay, here's an Alex problem in our kinetics homework. These can be tricky. I think you have to have your A game when you do these, and you just have to pay very close attention and make sure you do everything right, because these can be somewhat involved. So here's the question. Nitric acid is a key industrial chemical used to make fertilizers and explosives, and the first step is to make nitric acid is the oxidation of ammonia. And in this reaction, ammonia reacts with oxygen gas to produce nitrogen monoxide and water. And then it gives us this scenario. So suppose this chemical engineer studying this catalyst for the oxidation of ammonia finds that 444 liters per second of oxygen are consumed when the reaction is run at these temperatures, 277 degrees C and 41 atmospheres. That's the pressure. Calculate the rate at which nitrogen monoxide is produced. Give your answer in kilograms per second. Okay, so that's going to be good to know, and be sure that your answer has the correct number of sig figs. Well, I'm looking at the sig figs, and I'm thinking that likely we're going to have 2 sig figs in our answer, so I'm just going to keep that in mind. And remember, we want to be in kilograms per second. So the first thing that I want to do here is just make sure I get the chemistry right. And so what we have here is we have that ammonia, NH3, okay, plus oxygen, O2, is going to yield to us nitrogen monoxide, NO, plus water. Okay, so that's the chemistry that we're told that we have to do. Okay, so the first thing I want to do is I want to make sure that I balance this, and so when I kind of look at this by observation here, then I can see here that likely we're going to be 4 here, we're going to be 4 here. It's going to mean that we need 6 here to get those hydrogens right. And then that means the oxygens left. I need to have 5 of those. Okay, so I'm pretty sure this is my right chemistry that's going to go on. And so when we write those rates, okay, we want to write like this. If you remember from our lecture, that, I'm going to look at that coefficient right there. So 1 over 4, okay, and that's going to be consumed. So I put a negative there because that ammonia is going to be consumed. Okay, times the change in the concentration of NH3 with respect to time. Okay, that's going to be equal to a negative 1 over 5. I'm going to move on to this. That's the change in O2 with respect to time, and that's going to be equal to, I'm going to work on this, 1 over 4 times the change in the concentration of NO with respect to time, and that's going to be equal to 1 over 6 times the concentration of H2O with the change in that with respect to the change in time. Okay, so here are my rates that I'm going to be dealing with right here. Okay, so as long as I wrote those correct, I'm probably in good shape. Now it's telling me, let's read this again. Okay, they finds that 444 liters per second of the oxygen, the dioxygen, is consumed. So it's given us some quantitative values right here when the reaction is run at these temperature and pressure. Okay, and it's asking us to calculate nitrogen monoxide. Okay, so it's giving us the oxygen and it wants us to deal with the nitrogen monoxide. Okay, so that says then, I'm just going to take those 2 out, that minus 1 over 5, change in oxygen, is going, with respect to time, is going to be equal to 1 over 4 change in the concentration of nitrogen monoxide with respect to time. So, since we're going to be given this in per second, so this is going to be in units of seconds, so I know what the change in time is. So I can calculate this. That's going to leave me then with one unknown, and that is this nitrogen monoxide. So how am I going to do this? Well, it's given me a temperature and a pressure. It's giving me a volume here. Okay, so we're going to have to go back to last semester and know that PV equals nRT. Okay, so I've got pressure, I've got volume, I know R, and I've got a temperature. So I can calculate the number of moles of that oxygen. So I'm just going to rewrite this to say N equals PV over RT. So I can plug this in now. So my pressure is 0.41 atmospheres times the volume, which is in liters, 444 liters, divided by R, which is 0.08206, times the temperature. Remember, temperature has to be in degrees Kelvin. So I'm just going to do that up here. It's going to be 277 plus 273.15. And so when I do that, it's going to give me 550.15. So my sig figs are going to be right there. So I got 3 sig figs there. So 550.15. So times 550.15. Okay. So that's when I do those calculations, then that is going to leave me with, I'm just going to do that, 4 points on my calculator, 0.323 moles of O2. Okay, that is the number of moles of O2 in those 444 liters that are formed each second. Okay, so now I can come back and start using my equations right here. Okay, so now I have minus 1 over 5 times the change in the concentration. Well, we have those moles right there, so I'm going to put here those 4.0323 moles. That's for every 1 second. And that is going to equal 1 over 4 times this nitrogen monoxide, okay, for that same 1 second. Okay, so now I can get that the nitrogen monoxide is going to be equal to, I'm going to, when I do the algebra, this is just algebra, that 4 is going to come up over there. So that's going to be negative 4/5. Remember, that means that ammonia is being consumed. What's that? That's what that negative means. Times 4.0323. I'm just doing the algebra of this expression right here. Okay, I'm just doing that right there. Okay, so when I do that algebra, then that is going to be equal to 3 point on my calculator 2 carry a few more 584 moles of NO, and that are going to be formed every second. Okay, so those are going to be formed every second. Alright, but it's not asking for moles. Okay, what's it asking for? Kilograms for every second. So let's just go ahead and do some conversions here. So I'm just going to bring that 3.22584 moles of NO every second. Okay, so when I do that, I know that in 1 mole there are going to be 30 grams of NO. Okay, but it doesn't want it in grams. Remember, it wants it in kilograms. So that's going to be 1,000 grams in 1 kilogram. Okay, so when I do those maths right there, that's going to give me 0.09677, okay, and it's going to give me those number of moles. I'm sorry, kilograms. So those units are in kilograms. So I know that my grams cancel out, my moles cancel out, and so it's giving it to me in kilograms. Okay, now let's just worry about those sig figs. Remember, we go back up here in our multiplication, and we know that we have 2 sig figs. And so when I bring that to 2 sig figs, the answer to this is going to be 0.097 kilograms. Okay, so that is going to be the answer that we should put into this Alex right here. So again, just a really quick review. Get the chemistry right. Make sure you balance it right. Once you balance the chemistry, then write the correct rates that are going to be for each reactant right there. Okay, once we do that, then we take our values here, and we use the ideal gas law to get moles. Once I get moles, then I can just use these rates, set 2 that are going to be equal together. And how did I know which 2? Well, because it gave me the oxygen and it asked me to figure out the nitrogen monoxide. That's why I chose those 2 and set those equal to each other. I calculated my oxygen right there. That leaves me with just one unknown. And when I have that one unknown, that's easy algebra that I can do. Once I get that unknown there, then I can get the moles of nitrogen that are going to be produced in that 1 second. Once I do that, then it just asks me to convert those into kilograms, and we've been doing that for almost all of our chemistry. So this is doable. It can be a bit challenging to keep everything straight. So I think we have to answer a few in a row correctly. So again, just be very, very careful when you do these. Follow this type of algorithm that I've done for you, and you should be in pretty good shape to do these.